Previously, we've talked about alternating series, and in particular, we had a criterion for when certain of these type of series converges. If for all indexes I, or at least some index I beyond some threshold value, capital N, the AIs are positive, decreasing, and besides those two conditions, the AIs approach zero as the index becomes indefinitely big, then we know that the alternating series converges. For the entirety of this video, I'm going to assume that the nice conditions are true so that I know my series automatically converges. This business about decreasing the AI plus 1 being less than AI is going to tell us something very interesting. To convey the idea, I'm going to think of calculating the first 5 partial sums and then ask myself, what's going to happen after that? Partial sum S1 is just A1. A1 is positive, so if 0 is here, S1 is off to the right some distance. When I calculate S2, this will be A1 minus A2. The A numbers are positive, so S2 will be smaller than S1 is, but since A2 isn't as big as A1 is, it doesn't push me all the way to 0 or beyond. S3 is the positive number A3 more than S2 was, but on the other hand, A3 isn't as big as A2 was, so that I started here, I subtracted A2, then I'm going to add a positive number that's not as big as A2 was, which means I'll get an answer that's bigger than S2, but not as big as S1, or any number further to the right. Imagine continuing this procedure until you calculated S number 5. When I calculate S number 6, I'm going to have the same terms as for S number 5, except I will subtract away A number 6. When I calculate S number 7, I'm going to add A number 7 to S6, which will give me a sum that's bigger than S6, but not as big as S5. When I calculate S number 8, wherever S number 7 was, I'll move A number 8 to the left, but I'm still trapped between S6 and S5. In fact, all future partial sums are going to be between S6 and S5. If all of the partial sums after S number 5 are contained within the interval from S6 to S5, then the limit of those partial sums must be in there as well. Remember, we're assuming the nice conditions on the alternating series, which guarantees that it converges. So whatever the limit is of the partial sums, I could call it capital S. Capital S is somewhere between S number 5 and S number 6. Capital S is within a distance of A number 6 of the partial sum that we calculated. In the preceding discussion, there was nothing special about the fact that it was the fifth partial sum that I was looking at. The same kind of argument would work if I were looking at the 10th partial sum or the 14th partial sum, or whichever one of them I decided to look at. So in one of these nice alternating series, if I calculate a partial sum, this in a sense is an approximation to the value of the series. I can give you an estimate for how good it is by looking at how big the next term in the series is. For example, if you look at the sum I equals 1 to infinity, negative 1 to the I plus 1 over I factorial, the first few terms of which are 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial, and so on. This is an alternating series. The individual a numbers get smaller and approach 0 as the index becomes large. This is a nice alternating series. I automatically know that it converges. If I approximate the value of the infinite series by this partial sum, this is going to give me some number. It's going to be an estimate for the value of this infinite series, and I guarantee you that that estimate differs from the true value by no more than this amount. One over 6 factorial, though, isn't a particularly tiny number, and we would like the difference between our estimate and the true value of the series to be tiny. As another example, I want to look at this kind of series, which we talked about before. This is obviously one of these nice alternating series. I want to think about this. If I were to include terms out to the 1 over 10 factorial, how different could that be from the actual value of the series? According to my calculator, the partial sum is 0.540302303.8. According to this thing that we figured out, the difference between this and the true value of the series can't be any bigger than the next term that we would add on. Using my calculator again, that works out to be about 2.08 times 10 to the minus 9 power. The reason that I wrote all of those digits down is all of those digits are supposed to be correct. The reason that I didn't write all the digits in the 2.08 number down is that they're not very important to me. It's about 2 times 10 to the minus 9 power. The minus 9 is the important part. I've been editing away on this video, and it was only at the end that I noticed that my customary farewell had been omitted. So I'm recording this with Audacity instead of the recorder in OBS. It'll be interesting to see if there's much difference in sound quality. Anyway, I hope everybody has a good day, and I'll talk to you again soon.